This is part of the Montpelier Place series. My name is Erica Hampel. I am a student with UVM in the Field Naturalist program, and I'm organizing the Place series, which this is the 7th event in, I believe. So thank you for, if you've been to the past events, thank you. If you are coming to if you're interested in coming to more, there's going to be one more in this series, and there's a question box in the front for if you want to see something new come out down the pipe. I want to thank our sponsors, the Hunger Mountain Co-op, the Ben & Jerry's Foundation, and the Vermont Community Foundation. And I just want to introduce our speaker today, who is Sean Beckett, over here. He's going to talk to you. And then lead you on, hopefully, you can come tomorrow, too, for a really great field walk at 9 in the morning. Sean works at North Branch Nature Center here, and just really excited about rocks. And so hopefully you can share that excitement with you. And I'm just going to let him take it away.
Thank you. All right, hello everybody. It's a pleasure to see you all. Thanks for coming out to talk about rocks all night. So I have some notes to myself here, which I need to make bigger. Hang on 1 second. Well, guess I won't. The first note to myself is to tell you where we're meeting tomorrow. So I don't forget. So if anyone wants to join us for the field walk tomorrow, we're going to meet at, the field walk is 9 to noon, and it's going to be starting at Gateway Park. So if you go down Route 2, past Greenmont Cemetery, just across the street from Greenmont Cemetery, there's kind of like a parking area that's actually called Gateway Park, right under the interstate. It's like a fishing access. There's lots of place for parking there, so we'll convene there. And we're going to walk across into Greenmont Cemetery and check out some escarpments at the back of the cemetery. So we're just meeting at Gateway Park. And then we're going to travel to a couple other places around town over the course of the morning. But if you want to join us, 9 o'clock at Gateway Park is the place.
Should we encourage carpooling?
We should encourage carpooling, Paige, yeah. So if you know anyone else in the room who might be going, see if you can carpool to Gateway Park. We can also carpool Gateway Park would be a fine place to leave a car too if folks want to carpool from there across town after that. We'll be staying within the city limits pretty much the whole morning. So, sound good? Okay. My name's Sean Beckett. I'm the program director here at North Branch Nature Center. I teach I'm a graduate of the UVM Field Naturalist program as well. I teach with the Vermont Master Naturalist program. Many of you have done this program or are in it currently. Raise your hand if that's the case. 1, 2, 3, 4. Nice. I've found that in my explorations as an ecologist, I keep coming back again and again to the fact that rocks are really the most important thing out there. Everything can be explained by the geology, by what's going on underfoot. There's, as a botanist, we can walk into the woods and we can see particular kinds of tree species and expect where they're going to be growing. And if we see a maple tree, we know there's going to be, probably a yellow birch tree growing nearby. There's certain patterns that we can expect to see as ecologists when we walk around our natural landscape. But there's also incredible connections between our geologic story and our natural landscape, or I should say like the botanical world on top of that. And I think in certain places, if you were to tell me or to tell someone who knew these things what kind of rock you were standing on, not only could that person then even imagine what kind of forest was growing on top of it, but could even imagine the sound of the bird songs that were singing on top of that. So when I think of the Moncton Quartzite Formation in Burlington, I am listening to the sounds of wood thrushes in my head. And when I think about the Moortown Formation, phyllite formations in western Montpelier, I'm thinking about the sounds of hermit thrushes in my head. I'm thinking about the hemlock trees that are growing around. So I just love the geological determinism of it all. What's underfoot really totally explains what's happening around us. And that doesn't stop with the natural world either. I would argue that our built environment can be tied back in many ways to what's happening geologically in an area. And one of the things I want to introduce tonight, just plant the seed, is that many of the decisions we've made around Montpelier's architecture and what we're building our buildings out of and why and where can be tied either in large part or small part to what's going on underground. And I just think that's a really cool idea, and it makes our city unique to place, right? I should also take a moment to acknowledge that we are on Western Abenaki land, and although tonight I'm introducing this story to us in terms of how geology is connected to our way of life, but this is not news to the Abenaki people who, for 12,000 years, geology has been part of their way of life, and this is not a new story to them. This is a 12,000-year-old story, and so I'm inviting you to start the story tonight, and we're going to talk a lot about we're going to go back into the past 500 million years, and we're going to go fast forwarding up to today and looking at how some of our buildings are where they are. So, this is a beautiful watercolor by a field naturalist alumni. Claire Dacey is her name. And this is nice and representative of the parts of the earth that we tend to think about, are the parts that are in color here. The parts that we can see, the waters, the trees, the roads and buildings and houses, the birds, the sky, right? But those are all layers of our landscape layer cake. But those layers go underground too, into the ground. When we talk about geology, just to get us all on the same page here, we're talking about one of two things. When we talk about geology, we could be talking about the bedrock, right? And bedrock is beneath everywhere on the planet. So whether you're standing here, whether you're in the middle of the ocean, if you go down far enough, you're going to hit bedrock. In many cases, your foot is already on bedrock as soon as you walk out the door. Or if you're up on top of a mountain or on the edge of a ledge, you're touching bedrock. Rock that is connected contiguously all the way through the crust of the earth. In many cases, that bedrock is buried under tens or hundreds of feet of sediment or beneath hundreds of feet of water. But if you go down far enough, you're going to hit bedrock. So when we talk about geology, we could be talking about bedrock. We could also be talking about superficial stuff, or glacier junk, I kind of call it. So anything that's not nailed down into the bedrock is susceptible to be moved around by all the dynamic forces in our landscape. So glaciers coming and scouring the landscape, streams eroding away our mountains, moving silt and clay and cobble and sediment across the land, spitting it out into huge piles here and scouring it away there, and leaving sediment of all different sizes, from as fine as flour to boulders as big as houses, kind of strewn about our landscape in non-random ways. So geologists really have two things at once to study: the bedrock and then all the superficial stuff on top of it. So when it came to thinking about how we would break down tonight's talk, it made sense to do this in two acts. Act 1 is going to be about the bedrock, and Act 2 is going to be about all the superficial stuff sitting on top of it. So Act 1 we're going to call the geologic frontier of Vermont, because I'm going to argue that Montpelier is the geologic frontier of Vermont. It's a very interesting place geologically, and it's very apropos that the seat of state government sits right here. In a way, Montpelier's bedrock geology is descriptive of the entire story of Vermont's geological history. In Act 2, we're going to call When the Earth is Flat, and talking about how the glaciers and the ice ages have shaped a lot of our landscape around us. So going into Act 1 here, we have, we're going to break this into basically three scenes. There's three things that I want you to walk away with in our bedrock geology story. And there's going to be three different types of rocks that you're going to hopefully be familiar with and be able to recognize when you see after tonight. And these three different types of rock represents three different scenes in Vermont's bedrock geology story. We have scene 1 is the formation of the Green Mountains. This event was called the tectonic orogeny. An orogeny is just a fancy word for a mountain forming event. Scene 2 is when Montpelier loses its beachfront. Did you know that Montpelier was beachfront property at one point? So scene number 2 is the Acadian orogeny, another mountain forming event. And then scene number 3 is all the little granite bubbles, all the volcanics that we have strewn about central Vermont. We'll talk about that too. Now, it's always a good idea to get your bearings when talking about geology, because we're talking about things that can happen over such grand timescales that it's really hard to wrap our minds around the scale of it all. And so I love this figure because this basically takes a timeline of the age of the Earth and it wraps into a big spiral so you can actually fit it in a slide. So the Earth is 4.6 billion years old, and that's right here in the middle. And if you unwind this all the way, we go 4 billion years before we get to right about here where the color starts changing. And this, I know you can't read this, it doesn't matter. It says Cambrian. The Cambrian era right here is where it starts changing color. And that's where we're going to start our story, is right here. The story of Vermont's bedrock geology, as we know it, starts here and it works our way towards the present. Another kind of background thing that is important for us to all be on the same page about is that Earth's geology is a very dynamic thing. The Earth is made up of tectonic plates that are kind of like jigsaw puzzle pieces that are floating in water, a sphere of water, right? And really they're floating on a sphere of magma, molten magma. And these puzzle pieces are being pushed and moved around all the time. Not very fast, about the same speed at which your fingernails grow, is how fast these continents are moving around. But over the span of millions or even billions of years, these continents can really become reshaped and buried and exposed and change and move so that the Earth's continents, as they would be here in the timeline, are going to be totally unrecognizable to us now. So we're starting the story here 500 million years ago at kind of the edge of the spiral, because if you go much farther back than that, we just can't really keep track of what things look like because all the dynamic forces have kind of erased, all the chaos has erased what was before. So I want to share now a great video that is a diagram of the last 500 million years of geologic time. And let's cross our fingers that this works. This way. And would you mind getting the lights for us there in the corner, Nona? Other side. Yep. Perfect, thank you. What's that? Sound is off? Yep.
It'll sound back on the bottom. You click that, turn the sound on.
Oh, I don't want the sound on. Yeah, makes sense. Yeah, I'm going to have the YouTube do the talking for the rest of it. So, this is going to be, kind of, as we know it, the movement of our continents from 500 million years ago. This is really the story of Vermont's bedrock geology. So, things are moving slowly here, but I want you to find North America. We're kind of below the equator on its side, 520 million years ago here. And you'll see that Vermont over here is underwater. We're not land yet. This is where Vermont would be, but it doesn't exist yet right now. But this here is the tectonic plate that we sit on, Laurentia, it's called. And what's going to happen about 500 million years ago is this pile of volcanic islands is going to move towards the edge of Laurentia and slam into it. And when it does, there's going to be this mountain range right here that starts to form and come into existence. See that? You just watch the Green Mountains form right there. But now what's going to happen is there's going to be a quiet period for about 30 to 50 million years where nothing's really happening. We have this nice ocean out here that's getting narrower and narrower as this continent right here. This is kind of a proto-European continent called Avalonia. And the tail of this continent is going to come in and whack into the edge of Laurentia in kind of a multi-car pileup sort of situation here, all right? And the forces of this, Avalonia kind of ramming into here are going to put the rest of Vermont in place. So everything east of the Green Mountains. So right now, these Green Mountains are basically dropping off right into the water. And if you were sitting on top of Mount Mansfield, well, one, you'd probably be 20,000 feet in the air because this was a tremendous mountain range at the time. It's had 400 million years to erode, right? As you looked off to the east for 400 million years, you'd see this continental landmass coming towards you and slamming in to the edge of the continent. So watch for that. Brace yourself. So now we welcome eastern Vermont and New Hampshire and Maine to New England.
Is that Africa, one of those that slammed in?
No, that's down here. The map projection is really weird to just show North America, but Africa is actually down here, and that has nothing to do with our story. It kind of whacks into the south of Florida at some point. But really, right now, up in Vermont, nothing's happening. We are landlocked, or I should say, we are far from the continental, or from the tectonic plate boundary. So all this moving and everything that happens after this point in the history of Earth's plate tectonics are irrelevant to Vermont because it's happening way over there. We're no longer right at the edge, the active edge of things slamming into each other. We are landlocked with New Hampshire and Maine off to our east at that point. So things get pretty quiet here in Vermont. Meanwhile, the southern Appalachians are forming and growing. All sorts of weird things are happening. This is Pangea. I'm just kind of zoom forward a little bit here. This is Pangea, right? One of the supercontinents, most recent supercontinent, where everything was kind of glommed onto. All the continents that kind of found themselves. But again, Vermont doesn't really care. It's kind of over here. It doesn't know that Pangea is happening and all this kind of stuff, right? We are pleasantly in the midst of, we're just out there in the middle of the continent. I'm going to back up and just play that first bit again, just so that you can see it again with some context now. And shout out to what's this fellow's name? Scotese, out of University of Chicago and University of Texas, Arlington, who created this paleomap project, these great figures. So we have this island arc here. This island arc is kind of, think about it as like Japan, like the islands of Japan. These volcanic islands at the very edge of a major tectonic plate margin. And so this whole Proto-European plate is coming towards Laurentia, and it will slam into it. And this is the tectonic orogeny, scene 1. Okay? Now we have the greens, and now we have this trough closing. The Green Mountains are eroding away now into this trough, and then Avalonia comes in, and it scrapes that trough back up against the edge of North America, and we end up with our eastern Vermont.
Is the light blue this shallow water?
I think the light blue is just shallow water, yeah. Yep. And this is a great diagram, at the large scale of seeing what's going on. If you were to hold up a magnifying glass, it would be a little bit off of what's actually happening, but it's pretty darn handy to show.
And it's all below the equator?
At this point, all this is happening around the equator. Yeah. So this is a very tropical. Well, this is also 500 million years ago, so we didn't exactly have, forests and whatnot, but it was around the equators. Yeah. Christopher Scotese, paleomap project. I'll just put that back up here. Bear with me while I figure out how to go back into PowerPoint here in a way that you can see and I can see. Folks, I'll just need 1 second here. I had to restart this because I was confusing the computer by trying to do a PowerPoint while streaming a YouTube video. a good sign. I can't see my speaker view. No, we'll go with it and see what happens. Okay. Nope. Shoot. One more second, folks. Sorry about this. Too complicated for my own good. All right, we'll go with that. Hey, all right. Okay. So I just want to show you kind of a cross-section diagram of that story basically happening. We have Proto-North America over here, Proto-Europe over here. These plates are converging. If we are over on the eastern edge of New York, we'd be on the shores of this Iapetus Ocean, looking at this volcanic island arc coming towards us here, forming the tectonic orogeny. Now, this is where things get interesting. So, if you are standing at the shores of Lake Champlain, let's say, and you walk into the water, you're standing in sand, right? You're at the beach. But you know that the farther you walk into the lake, the muckier and muckier and muckier it gets underfoot, right? That sediment size starts to get finer and finer and gloopier the farther you get into the lake. Where if you want a sample of really good, fine lake clay, you go out to the middle of Lake Champlain and you take a sample from there. The farther away you are from the shore, whether it's a lake or whether it's the ocean, the finer and finer the sediments are that are going to settle there. So the sediments that are eroding off of North America, off of Laurentia, into the Iapetus Ocean, are very different here than down here. When we're near shore, at a place that's near shore, we're looking at deposits of sand. We're looking at deposits, we're in a place that's very, has a lot of light penetrating, so there's lots of life, there's lots of coral, there's lots of invertebrates, mollusks with shells, things like that, algae, diatoms, lots of things that create limestone and limey stuff, right? The farther we get out here into the deep water off the continental shelf, this is where things like silt and clay are depositing. And it's so deep that there's no light penetrating there. We don't really have much life out here. So as the millions of years go by, sediment is accumulating off the shore. It's eroding off of the continents. And the sediment that is here is different than the sediment that's down here. These sediments are building up, again, over millions or tens or even hundreds of millions of years. So the sediment can be piled miles and miles and miles deep. And the weight of the sediment on top of itself, plus the water in the picture here, cements that rock together and lithifies it. Lithifies is a word that just basically means to become a rock. So the sand is lithified into sandstone. The limey stuff is lithified into limestone. Out here, that mud is lithified into mudstone, or shale is another word for that. Right? And so we have all these sedimentary rocks, layers and layers of it, miles and miles thick, that are forming over this time. And when this island arc comes in and slams into Laurentia, it basically scours and pushes all of this rock up with it. Kind of, I like to think of it as like if you were trying to plow a driveway and you push the plow into it and it piles up this big pile of snow at the end of the driveway. That is what's happening here, where you have the North American plate that's sliding underneath and subducting beneath the, should do it this way. Proto-North America plate is sliding down below the incoming European plate, and it scours and pushes those miles of rock up in front of it. And so what we see is that over here, this is the Champlain Valley, has just been added to Laurentia now from all these rocks that were pushed from near shore. And the Green Mountains is all this junk, all the stuff that was pushed up from farther deep in the water. And this volcanic island arc erodes away quickly. And basically, we're not very far from the ocean here. Montpelier is basically sitting right in here and looking off into the Iapetus Ocean. This is our bedrock geology map. Yes?
When you talk about sediment at that stage, what is it bits and pieces of different kinds of rock, or because it's not plant material or dead animals?
No, it's just sand, silt, clay, and dissolved dissolved calcium. Yeah, so it's all the stuff that's eroded off of the landscape into the ocean. So it's the same stuff that's that runs through any stream. Really, it's just sand, silt,
but
clay.
Because there are no animals and plants or anything, right? So it's all.
Well, eroding off of land is all sediments of basically what was weathered rock. So the landscape, the rock of the continent is weathering and eroding into grains of sand and grains of silt and grains of clay, which get swept downstream into the ocean and then get deposited out there. You're right that there isn't, there's not a ton of life yet on land. In the water, at this point, there is life, and so near shore, you do have a lot of coral reefs and that sort of thing. But yeah, the sediment is made up of weathered rock that's coming off the continent. This is northern Vermont. Just for context, Montpelier is this yellow circle in the middle. And here's Burlington right here, Colchester Causeway, South Hero. So this is just northern Vermont on this bedrock geology map. And a huge kudos to our state geologists in the Vermont Geological Survey, because they have it a lot harder than, say, like Kansas. If you look at the bedrock geology map out in other places, it's not this interesting. I don't know this for sure, but I might wager that Vermont has for its size, has the coolest and most complex bedrock geology story of any 6 million acre chunk of this country. So we have the Champlain Valley over here, and we have all this stuff is the Green Mountains. Okay? If you want to go in Vermont and find some really good limestone or really good sandstone, you go to Burlington, you go to Colchester, you go around here. These rocks here are these rocks here, all these nearshore things, right? When we go into the Green Mountains, we're looking at rocks that are metamorphosed mudstone that came from, well, I won't go too far back, but metamorphosed mudstone that came from way deep in the Iapetus Ocean. And so this is mud that's been turned into shale. And shale, when you metamorphose shale, you call that rock either phyllite or schist or slate, depending on how much metamorphism it gets. I can talk about that later, or tomorrow, actually. It'd be a good time to talk about that. But basically, the rocks that we have in the Green Mountains are these deep water, really old rocks that are put up there by this tectonic orogeny event. Yeah, Deb.
When we say mountains, are they tall?
They're huge, yes. Hold that thought for 2 slides. Yeah. Maybe 3 slides.
Where's the brother?
We're not there yet.
Oh.
That was just scene 1. We're only at so right now. So all this rock here, the Green Mountains. What this looks like is this. Can we pop the lights back on, Nona, please? If you have a rock, can you hold it up? Or look around on the chairs next to you, and if you see a rock, hold it up in the air. I handed out like 10 rocks. I know they're not there.
Too late to get in pockets.
All right, winner. This one. And you know there's got to be more. Oh, that one. Let's see. Oh, that's not it. Okay. So this rock that is basically the western half of Montpelier and throughout the Greens, it looks like this. It's kind of bluish, kind of greenish. It is called schist or phyllite, depending on exactly where you're standing, and it is a metamorphosed mudstone. Its source are from ancient muds and clays that are accumulating in the deep water way out far from shore. This geologists call this formation the Moortown Formation. So Montpelier, right here, the western half of Montpelier, all this beige stuff is this bluish-green rock. So I'm going to pass this around and convince yourself in this weird light that it's, or the lights that are soon to be off again, that this is a bluish-greenish sort of rock. And maybe we can pass around this other example of it too.
Are these the rocks that are in downtown, like on the North Branch River?
So these came from Hubbard Park. These, in fact, came from Erica's field walk last week. So if you are, and I'll explain exactly where these are, but if you are really anywhere in the left half of Montpelier, this is the rock that you'll find.
What's that?
What's that? Say it again? Yeah, so the Green Mountain, I mean, so...
What was the question?
So the question was, how did the Green Mountains, is the fact that this rock is greenish blue, is that how the Green Mountains got their name? And I would like to think so. I think it's just because they're forested and green and that sort of thing. But the rocks do kind of have this greenish, bluish kind of hue to them. And Nona, would you put the lights maybe halfway down? Yeah, great. So these, this is Greenmont Cemetery. It's a rock escarpment here. If you go anywhere around most of Hubbard Park, looks like this as well. Here at the Nature Center, it looks like this. So greenish, bluish rock, kind of slabby. Let's hold that thought and kind of put a mental bookmark on what this looks like. Tomorrow we'll actually explore this. You'll get to see it up close. Okay? Now Deb's question, how big were the mountains? So these mountains were huge. The Green Mountains have had 500 million years to basically erode away, and they're still this big. So these mountain ranges would have been the size of the Himalayas at the time that they were at their peak. And so at this time, after the tectonic orogeny, Montpelier was sitting right at the shore of the Iapetus Ocean with a giant Himalayan-sized mountain range just out back. So if you were to walk up to the top of Hubbard Park, it would be a much longer walk back then, right? And for the next 30 to 50 million years, nothing was happening. Montpelier was just enjoying itself here on the shore, and things were eroding away. As soon as mountains form, they start to erode back into the sea, right? And so while that Avalonia was kind of coming in and getting ready to slam into Montpelier, all of this was eroding away. In the same process we were talking about before, where this sedimentation happens, was happening, then too. Except now Montpelier is right at the shore here. And all this nearshore sediment is made up of everything that just eroded off of the Green Mountains. All those mountains that just got pushed back up, all the most easily erodable, easiest to dissolve minerals, rocks were the first things to kind of melt off of those and find their way back into the ocean. So a lot of the stuff that had calcium carbonate in it that was pushed up real high was the first thing to dissolve and wind up back in the ocean. So anyway, all these sediments here that then lithified, and we had another one of these mountain forming events. Where here we have the Green Mountains and that first volcanic island arc that slammed into us. Montpelier is here, and we have this trough of the Iapetus Ocean that the mountains are eroding into. A new sedimentary rock is lithifying. Then Avalonia comes in and scrapes it all back up against Montpelier. And now, once that happens, if you're standing at the top of Hubbard Park looking east, you're no longer looking out into the Iapetus Ocean, you're looking out across eastern Vermont, and way out in the distance you see New Hampshire and you see Maine. So here we are in Montpelier. Everything to the west is all kind of green mountain formations. Everything to the east is all the result of the Acadian orogeny. And these rocks here look totally different. They look like this. Right? This is not greenish blue. These rocks are charcoal gray. They're black when they weather. They weather oftentimes it's like rusty orange color. Right? They're a really striking, beautiful formation, and it's very variable. And it's really variable because remember, all this stuff was eroding off of the Green Mountains into the Iapetus Ocean. And that was a catastrophic. It was near shore, and it was a very kind of chaotic time. You know, one day you have a big landslide, it dumps a bunch of sand into the ocean. Next day, you know, something else happens and a big landslide happens over here. Then maybe nothing happens for a while and kind of clay just kind of settles down. So it's just a very dynamic environment near the shore of this eroding Green Mountain range. And as a result, the rocks that we get are also very dynamic. If you are standing at one point, at one part of this ledge here, you're looking at a rock that could be compositionally very different than, you know, 10 feet away. Because this is just a very active environment. The depositional environment when that sediment was first going down was very active. So, Nona, thanks for standing there and doing the lights. Lights on, please. Hold up your rocks if you still have them. Great. So, I know there's more than that. But let's see. So you have the Moortown Formation. Paige, you have Moortown Formation. This here is the Waits River Formation. This is the other kind of rock here. We can pass these to you. There's some more chunks of the Waits River Formation. So you can look carefully and see that there's little bits of rusty bits in there, but largely it's black, charcoal gray. Hard to see in this light here, but. So that's scene 2. In scene 3. Oh, yeah, sure.
Well, maybe you're letting me. There's a bedrock map. What was the big red?
Oh, that's perfect lead in. Okay, you might notice that there's these big red blobs all over. Is that what you're wondering about? Okay, so we have this like really north-south running geologic map, right? You can just picture this being accordioned together as a result of those mountain-forming events, right? You understand now why everything is oriented north-south because of this dramatic pressure of the Tectonic orogeny and the Acadian orogeny. And yet then we have these weird blobs of this orange-white dotted stuff in the map. That's the volcanic stuff. Yeah. So, meanwhile, while all this was happening with the Acadian orogeny, whenever you have a plate boundary that's subducting beneath another plate, that's an immense amount of crust that is being burned and melted into the mantle down below. And as that all melts, it creates an incredible amount of pressure. And so the magma that is being formed from this just melting into the mantle starts rising back up through the crust. And it's burning its way up through the crust towards the surface. It's really hot, it's really gaseous, it wants to kind of move upwards. And so it just kind of melts, as it melts, it kind of moves its way up like the bubbles in your soda, right? Through the earth. And if that magma makes it all the way to the surface, then we know that as a volcano. But more often than not, it kind of peters out before it gets there. As it gets closer and closer to the surface, it's cooling down more and more and more to the point where it's not really active anymore, and it just kind of settles in place underground. And you end up with these little pillows, or like balloons of magma that are beneath the Earth's surface. These are called plutons. And these are granite. Granite is the igneous rock that you get from this process. And granite is also a very strong rock compared to the limestones and sandstones and schists that we've been talking about. And so over the span of hundreds of millions of years, as the whole Vermont landscape erodes away into the ocean, it reveals these plutons that don't erode away as easily.
So any of these rocks just become granite by virtue of having been superheated and pressurized?
Granite is basically cooled magma. So, and any rock can become magma once you melt it. Yeah.
The crystals you see in granite are what develop as it cools.
Yeah, thanks. And so these are both kind of heavy. Yeah, this is light enough to pass around. So here's a big hunk of granite, and if you look at this carefully, if you're willing to take that thing, right? You can look at the crystals formed in there, and you know every granite and we'll circle back to this in a moment. But every granite outcrop, every pluton has a different kind of signature of the size of those minerals and also the composition of them, the ratio of feldspar to quartz to mica, or things like that. And so you can tell where a chunk of granite came from if you can match it to the chemistry of the surrounding plutons. So every one of these orange bubbles is a magma pluton that has a granite pluton that has been revealed through erosion of everything around it. Yeah, no.
I understand that the granite is magnet. Granite, it was magnet. What I don't understand is why is it when you cross from the feed up in the west, you cross the Winooski going east to Plainfield, it's all granite over there. And the division is the river. What is the river like? Or is that later?
No, I mean that's a good question. So I'll repeat that to the best of my ability so that this microphone can hear it, and also you can hear that. So Nona was noticing that when you cross into Plainfield, suddenly you end up in granite land. Groton State Forest, right? All that is all granite. That's what this big thing here is all Groton State Forest and Plainfield and whatnot. And it's a sudden transition because the edges of those plutons are very discrete. Now, why is it a coincidence that the river happens to be the thing that delineates it? Now, without going there and looking at an escarpment on one side of the river and looking at it on the other, I don't know. But rivers tend to find contact points between geologic layers because those are point of weaknesses. And rivers, when they find a spot of weakness, it can erode in there, and then kind of like a knife through butter, it just kind of incises itself into a path that it likes. And so it could be that the edge of that pluton is just a nice space for that, where that river kind of tucked into and is followed. Okay, so quick Act 1 recap, and then we're going to go on a tour of some sites in Montpelier here. Montpelier is at Vermont's geologic crossroads because we are sitting at a spot where everything to the western half of Montpelier is all one type of very old rock. Everything to the east half of Montpelier is a much younger, very different type of rock with a very different story. And we have these granite outcrops kind of not in Montpelier, but all around us that contribute to our story as well.
So where is the division in Montpelier?
Oh, I'm so glad you asked that. Because that's exactly what I'm going to do next. I'm going to show you some zoomed in maps. And I'm going to do some zoomed in maps, and then we're going to go to a couple spots here. So first, I actually want to start with the orange bubbles and whatnot. You'll see that there's not a lot of orange bubbles right around Montpelier. We zoom in to Montpelier here. This is actually that line between the Moortown Formation, the Waits River Formation, that runs right through here, runs right through the middle of Hubbard Park. North Branch Nature Center is all Moortown Formation, but if you actually go across, like over the Vine Street Bridge, you're back in the purple stuff. If you're on, Franklin Street, it's all Waits River Formation. If you're over here, at CCV, it's all Moortown Formation, and it's a sudden transition. But I want to direct your attention there, down here, to this tiny little sliver of orange, right? Has anybody been there before? This is the north end of Berlin Pond, right there, cut off at the edge of the map. And if you go here, no, we take the lights, please. Thank you. So north end of Berlin Pond, this is Crosstown Road that takes us down to West Berlin. Just probably use this. And then right here is the parking lot for Boyer State Forest. This is all Boyer State Forest and Irish Hill Trails, Darling Hill Trails. And if you park here and you walk in, you're walking in through all that Waits River Formation, all the blue stuff, all that black, rusty-looking kind of slabby stuff. And then you hit this spot, and suddenly you come into this little pocket of granite. This pocket of granite that's maybe 3 times as wide as this building and a few hundred yards long, and that's it. Tiny little pluton that's been revealed, and it was known about. Because the West Berlin Granite Company set up shop here quarrying this tiny little pocket of granite for the span of about 50 years in the 1800s. And when you're here, you'll find this awesome little quarry pond here, spotted salamanders and Jefferson salamanders breeding here, FYI. There's little piles of granite tailings of blocks that they cut out that broke. So all over there's these big, rock outcrops of just, granite tailings. That porcupines and fishers are hanging out inside. It's an amazing place. And even if you haven't been here, you have been here. So this is State Street, the Episcopal Church on State Street, right? And this church was built from granite from that quarry. And so if you were to look up close at the rock, the granite that I'm passing around, it is going to be exactly the same as the granite up close on these stones on the Episcopal Church. So I wanted to start by talking about granite like this, just because Montpelier has such an important role in Vermont's granite industry. This is a slide I grabbed from Paul's talk last week, so courtesy of the Vermont Historical Society. But this is kind of looking down Stonecutter's Way, taken from, would this be taken kind of near where Sarducci's is right now, maybe? Looking down that way. So there used to be a really active granite finishing industry along the Winooski River once the railway went in here in the 1850s. And so, yeah, again, Montpelier doesn't have any granite, but a lot of granite came through Montpelier, and so as a result, a lot of buildings in Montpelier were able to benefit from that. Let's go back to the Episcopal Church. But has anybody walked around to the back side of the Episcopal Church? Fascinating. This is one of my favorite structures in Montpelier. Now, the framing around the edge of this chimney here are features of granite. You can kind of see that gray, these gray blocks, right? But everything else looks like bricks, doesn't it? But it's not brick. It's the Waits River Formation bedrock. And it just so happens that stuff is nice and slabby. When you crack it and break it, depending on if you're in the right spot in these formations, it breaks into a nice flat thing that you can pretty easily make into something that you could make a really sturdy fieldstone foundation or stone wall, or actually lay it like bricks almost in structures. So I haven't seen any other buildings in Montpelier that take advantage of this. Have any of you seen other places that utilize Waits River Formation rock in its construction?
Maybe foundations.
Certainly foundations. As I was wandering around Montpelier looking for this rock, I really wish I could have seen into the foundation of these buildings, because I'm sure that most of the foundations in our city are either made from Moortown Formation or Waits River Formation, depending on where you are. Does anybody have a stone foundation? And which one is it?
I never thought about it, and I'm going to guess that it's Moortown, but it's pretty great. Just by color.
Yeah. Are you on this side or that side?
I'm in the meadow.
So yeah, we're just yeah. So you could actually have either right there. I should just say that this little purple stripe down here that's like 100 feet wide. That's kind of an intermediary zone of that's basically, it's like the Waits River Formation. It behaved very similarly, and I don't want to. I'm just going to wave my hands and just say let's not worry about that right now. Yeah.
Well, I was just thinking, our house and many other houses on the north branch in town, the foundation of the riverside of the house is the stones that were placed there to make the channel for the river.
Yeah.
Sometime around 1860 or 65 or something.
That's a great point. That's actually a perfect segue into the next place we're going to visit too. So thanks. Oh yeah, so that's the rock from the Episcopal Church. Comparing that to the outcrop, we're going to go here tomorrow too. This is at the bottom of Sabin's pasture near the Pioneer Street Bridge. Right? Oh, we'll come back to the river abutments in a moment. Let's talk about Hubbard Park Tower. This is all Moortown Formation. See the greenish blue? And there's other stuff mixed around in here. But the Hubbard Park Tower, right, the construction of this started in 1915. We had a railroad, so we could have had things that were brought into town to build stuff out of, but no one is carrying rocks up to the top of a mountain to build this tower. Instead, they're dismantling the stone walls that were around the park and using those stone walls as the construction material for the tower. And so it's really fun to go to the tower and get a sense of what the local geology is like by just looking at the characteristics of these stones. You see, this is that Moortown Formation, it's that bluish-green rock, but we're looking at an angle of it that's really showing the metamorphic warps and things like that. As this rock heated and got pliable when the Green Mountains were formed, created these kind of ripples and whatnot. If you're in one of the rocks that's going around, if you look head-on at the rock, you can see these ripples too.
What's the name of that rock then?
It would be called either a phyllite or a schist.
Okay.
Yep. We want categories for things in terms of names of stuff. Like we want it to be either a limestone or a marble or a schist or sandstone. But in reality, you get these intergrades between all of them because it totally depends on just how much pressure this spot got versus that spot right next to it. And so I love the mess of it all. It makes it easy there. Do a lot of hand waving. We have these chunks of quartz that form in gaps and fissures and seams in the rocks. When the mountains form and the rocks cool and you end up with big cracks and voids inside the rock, groundwater fills in those spaces and the silica that's dissolved in the groundwater precipitates against the edges of those voids and fills in over time. Kind of like if you put like a popsicle in a sugar water cup and you leave it there for a while, you'll get that like sugar candy popsicle. Same thing's happening underground, but it's silica forming in the voids, and it forms these big quartz boulders. Right? So a lot of Moortown formation all over the place in this tower. Some sides look more weathered than others, and some of these rocks might be coming from a little farther east, into that purple slice as well. I don't want to belabor that point right now. Oh, actually, what I will belabor, though, is as kind of one cool thing is see how some of the rocks are very nice and rounded off, and some of them are nice and angular. So they're like a rounded rock, and this one is pretty angular. This one's pretty rounded. This is pretty angular, right? You can tell which rocks have been tumbled around by a glacier, and which ones haven't, by how rounded off they are. You know, this being underneath a moving glacier will do that to you over time. So some of these rocks you can tell were probably taken out of the soil that were till stones that were left there by the glacier. And others were rocks that were maybe chipped off of a ledge or outcrop nearby and then placed into place. So I invite you to scrutinize the tower next time you're there. National Life parking lot. The Waits River Formation. The black stuff that rusts a little bit orange, right? Right across the river from that same spot is the Moortown Formation at Vermont Cemetery. And when you look up nice and close, you can actually see those metamorphic folds in some places of when this was hot and under pressure like taffy as it was forming in the greens. Backing up, this is what that formation looks like farther back, and now you can really get a sense of that blue-green kind of tinge to this rock outcrop. Anybody here in 2005 see this happen? Off of Elm Street?
Oh, yes.
So this is Moortown Formation, showing its weakness when it is aligned in a certain way where water can get down in there and freeze and thaw and crack things off and cause rock falls. You're asking about why a house might be structurally unsound and near a ledge of Moortown Formation. This is maybe one of the reasons why.
Yeah. It's straight down that street on the other side of the river.
What's that? It's right across the river from this spot, yeah.
So the rocks on that ledge were part of Moortown?
This Moortown Formation, yeah, up Cliff Street and everything, yeah. So back to our bridge abutment, or river abutment things, right? I love this spot because this shows the entire bedrock history of Montpelier in one spot. Let's zoom in on this. Can folks recognize where this is? Betnales Beach Road, this is the Langland Street Bridge. Let's look closely. The bottom here, Moortown Formation. On top of that is stacked slabs of the Waits River Formation. On top of that are stacked slabs of cut granite. And I wonder if you could do a timeline of the history of embankment and raising of this embankment based on what kind of rock is being used. Right across the river from that is this is the other side, all big granite blocks here.
Sean, why would they put, if there was already Moortown Formation there as embankment, why would they have been put in?
I think they probably just used whatever was handy and lying around. So yeah, I mean maybe just down the road somebody had a pile of this stuff lying around, or there was a bunch of tailings of Waits River Formation that they could bring over on a rail car really quick or something. So it was convenient. It was probably the only answer. So yeah. So now with your trained eyes, you can tell that the Bethany Church is weird. It's a beautiful church. I love the architecture. Love it. But this ain't Montpelier rock, right? This is Moncton Quartzite, by the way, from Burlington, Colchester area. This was built after the Montpelier Railroad got its spur into town. So finally, at this point, once we got into the 1860s, you could build a building out of whatever you want because you can get rocks from quarries from all over the state to your city. prior to the 1850s, you had to use what was lying around, right? So use that, so scrutinize the buildings that you see in terms of the rock that you see, and you can maybe start to put some timelines on what you're seeing. I'll finish with this great photo by Wayne Fawbush that he posted on Facebook a couple weeks ago of the State House. Now, I think that the State House was sited where it is by geologists, because if you were to pick a perfect spot to perfectly represent the entire story of Vermont's bedrock geology, you would put the State House right here, because the boundary between the Moortown Formation and the Waits River Formation runs right across the middle of the State House lawn. If you walk out the western door of the State House, you are walking into Moortown Formation. If you walk out the eastern door of the State House, you're walking into the Waits River Formation. And I just think the odds of that are just so poetic. Love it. So
do you actually see that if you walk the trails behind?
If you kind of go and get a sense of what it looks like over here, and then go and compare to get a sense of what it looks like over there, you'll see the difference. Because it's actually in this weird purple zone, which is just kind of messy, it's kind of hard at this spot to really see a clear slice between the two. But there is a place that you can see a clear slice, and it's super satisfying. And that is, and maybe some of you know a different one than I do, but the place that I love is the northbound exit ramp into Montpelier. So let me take you on a trip there. So as soon as you get off the northbound exit ramp in Montpelier, notice the rock escarpment turning suddenly from the black Waits River Formation immediately into the blue-green Moortown Formation right there. So this is called the Richardson Memorial Contact, right? And I don't know why, but it has a name. And that is the spot where you put your finger on one side of that versus on the other side. You're spanning 60 million years of geologic time. One side of that, you're touching the rocks that were put there by the tectonic orogeny. And the other side, you're putting the rocks that were formed by everything eroding into the ocean after that, and then being shoved back up in the Acadian orogeny. Isn't that nice?
Yes.
Yeah, sure.
I did go after that newspaper article about rocks. I went up over there with the paper, and I walked halfway up the trail, and I looked, and I wasn't sure I was seeing what I wanted to see. Is it pretty visible if you go off the trail?
I did the exact same thing yesterday, where I went and looked to see if I could find the spot, because I was also intrigued by the Times-Argus article, which actually talks about that State House location, and I couldn't find a good, reliable spot. So it's there, but it's I couldn't see it. But also the rocks were wet too, and so once things dry out, and maybe in a different season it'll be a little more obvious. But we'll collectively keep an eye out for that.
What's the Times-Argus article?
Becker, who is his first name?
Laura.
Larry Becker wrote an article in the Times-Argus talking about basically talking about how the State House happens to be in a really unique place geologically. And he doesn't go into all the detail that I just bored you with, but does explain that these two sides are very different geologically, and that the State House is this cool dividing line, and suggests that you can go behind the State House to an escarpment right there and actually see that line. I didn't see it.
He said it was on the trail.
Okay.
I think he did. He was a state geologist. Yeah.
Well, I believe him, but I didn't see it. So collectively, we'll go find the spot somehow. Report back when you found it. So I want to get into our Act 2, which is a shorter act than Act 1, but very interesting as well. So we're going to talk about the glacier jump now, when the Earth, where and when and why the Earth is flat in some places. So we're going up a layer of our geologic landscape, and we're also going way to the end of the spiral, to this little gray blip on the very end, the last 20,000 years of the story of the Earth. Now, one thing that folks often get confused about when we think about geology, hopefully I can just put to rest, when we talk about rocks and bedrock, mountain forming and stuff like that, we're talking about things that happened millions of years ago and processes that took millions of years to happen. When we talk about glaciers and sediment and sediment deposition, we're talking about things that happened thousands of years ago and took hundreds of years or even tens of years to happen. So different time scales entirely. So we're going much more into our recent past here. And we're going to go to about 20,000 years ago at the peak of our most recent ice age. And at this time, all of the northern part of North America was under this big ice sheet called the Laurentide ice sheet. And we were covered under that ice sheet for quite a while. Vermont was entirely covered by a mile-thick ice up until about 14,000 years ago. And that ice, that glacier, as it advanced, kind of scoured everything. It kind of wiped the slate clean of everything that was above the bedrock at that time. Now, I couldn't find a picture of what it looks like to be under a mile of ice, but I wanted to find at least a picture of a lot of ice to hopefully convey something. So this is maybe 100 yards of ice, and what things might have looked like at certain times when you're looking up, the North Branch Valley or looking up Little River or something like that. But during the glacial maximum, the top of Mount Mansfield was under the ice. We were talking about a lot of ice. Now, when glaciers start to melt and they start to retreat, they don't, so glaciers actively advance and they push and scour things in front of them. But when they retreat, they don't turn around and march back north. They just melt in place, right? They melt from the edges inwards. Kind of like you put an ice cube on the table and you watch it melt. Like the center middle of that ice cube that's going to be the last thing to melt. It melts from the outside in. And so the edge of the Laurentide ice sheet retreated or receded to the north. And as that happened, watersheds would be impounded by those glaciers. This is actually this is a Google Earth shot from the Viedma Lakes in Argentina, which is a really cool example of this process that happened in Vermont 14,000 years ago happening today elsewhere. So we have this big glacier that's retreating out of this watershed. And as it's retreating out, this is the glacier up here, the glacier forms a dam that backs up a whole reservoir of water behind it. That reservoir is made of all the meltwater of that glacier, as well as all the rainwater and snowmelt and everything from the whole watershed here. And this lake will stay here, and it fills up until the water can find a different outlet through a different mountain pass to escape from. But as soon as this glacier retreats far enough out, then this whole lake will drop down like pulling a cork, like pulling the plug in the bathtub, right? Now let's look at our landscape here. 14,000 years ago, Montpelier is right here at the E of lake. There's the North Branch, Little River, Mad River, Dog River. What's the name of this river?
Jail Branch.
Jail Branch. Down to Williamstown. Anywho, so this is a glacial Lake Winooski that was formed by all of the glacier. So the ice had retreated out of the mountains, but there's still a vast amount of ice in the Champlain Valley that was acting like a big dam, blocking up this whole reservoir of water behind it. Right at about...
Lake Champlain is under that glacier?
Lake Champlain is under here, yeah. Yep.
Could you point Montpelier out once again?
Montpelier right there. Yep. Here's Worcester Range. So yeah, Montpelier. And so the Winooski River, all the water coming into the Winooski River Valley could not drain out the Winooski River into Champlain Valley. Instead, the water built up until it could find the next lowest mountain pass, which is here at Williamstown Gulf, at like 279 meters. So this is just another map of the same thing, glacial Lake Winooski. But then the ice retreated far enough out that the Winooski River, that this was no longer the lowest point in the Williamstown Gulf, but instead there was a channel that opened up where the Winooski River could get its way around the Huntington Gorge and out through Hollow Road into Heinsberg. Right here, there's a giant sand quarry right here in Heinsberg at the intersection of Hollow Road, and that's why. Because for a short time, the entirety of the central Vermont, bathtub was draining catastrophically right out of here and running into Glacial Lake, Vermont. So as the glacier retreated up the Champlain Valley, there was another glacial lake that was formed that was being backed up behind it, where the flow to the north was being blocked by the dam, by the ice itself.
What was the time scale for that drainage?
So, how fast did it happen?
Yeah.
So this happened in like days. It was, however long it takes that much water to get out of there. This wasn't something that happened over the span of years and centuries. This was like you don't want to be standing here. this was happening in hours or days that all this was draining out. It's a very catastrophic lowering, pulling the cork in the bathtub, right? And so then we ended up with this new lake level, this new step in the staircase of our glacial lakes, Glacial Lake Mansfield. And then the ice retreated far enough north that the Winooski could no longer needed this outlet here, and it can instead resume its normal course into the Champlain Valley this way, and the lake level dropped again to a lower stage of Glacial Lake, Vermont.
What's Montpelier again?
Montpelier is, where are we now? There's Little River, so we're here. Yeah, this is the North Branch Valley. We are right there, right now. Something like that. But this will make it easier. So here we are in Montpelier. We are up the North Branch, over there somewhere. This is Vermont Compost. This is, anyway, Montpelier, Terrace Street, Route 12 South, the solar panels behind National Life, like Child's Garden, right? Winooski River. So here we are. This is what would have been underwater, Glacial Lake Winooski. So this is just a short period of time, 14,100 years ago to 13,800 years ago. There'll be a test on that later. But no, this is like for 300 years, Montpelier was inundated up to this level, about 900 feet in elevation. It varies depending on where you are, based on the rebound of the earth from the weight of the glaciers. I won't get into that. But importantly, today when sediment runs off of our mountains, it runs downhill and dumps into the North Branch or into the Winooski River, right? So sediment works all the way down, and it pours into the river, and the river carries it down. But if you have a lake in the way, those tributaries come down and they dump their sediment wherever that lake happens to intersect that drainage, right? And so, and there was a lot less vegetation around at this time too. This was more tundra-like at the time. And so you have all this erosion, all this sediment running down the mountains, and as soon as it hits the edge of the lake, it dumps it out in place. So we end up having essentially like a bathtub ring of sand and gravel and sediments along the edges of our glacial lakes. And if you go to certain places in Montpelier, you can find those bathtub rings. But it's not just Glacial Lake Winooski. Once once that level dropped down one stair step, the lake level dropped down to here to Glacial Lake Mansfield level. For another 300 years, it stayed there at about 700 feet above sea level. And we get another series of bathtub rings there of sediment because now the tributaries can come down farther and they hit the lower lake level and they dump the sediment there. And then Glacial Lake Vermont dropped again. There are a couple intermediate stages between these two things that I'm just, for the sake of simplicity, just know that they're there, and know that as the lakes retreated, they didn't do it gradually over time. They did it catastrophically suddenly from step to step to step. And so we see stair steps of sediment in certain places. Now, this is complicated a little bit because we've had then 11,000 years of erosion happening that has obliterated and washed away and buried that evidence in most places, but there are some places where we can still see evidence of that, which we'll go into in just a second. In fact, we're going on that tour right now. So the first place we're going to go is up to the edge of the Wrightsville Reservoir, just looking north from the dam, because this is a good mental image of what it would have looked like back then. The Wrightsville Reservoir is at about 625 feet above sea level, so this is kind of between Glacial Lake Mansfield and Glacial Lake Winooski in height. But if you imagine kind of looking north, up the reservoir, this is kind of what the whole valley would have looked like. All central Vermont would have been kind of looked like a big reservoir like this. But we are stopping on the dam because we're actually on our way over to Ananda's Gardens. Okay? So we are in an incredibly hilly town, right? There's a lot of hills. There's a lot of mountains. There's a lot of uneven landscape. When you find something that is flat as a pancake, there's a reason for that, right? And Ananda's Gardens is surrounded by hills, but it is exactly 701 feet above sea level, and it is flat as a pancake. And I interpret that as where rivers are running into the shores of Glacial Lake Mansfield. So all of this is depositional of sediment being deposited into that lake.
So that would have been like a big beach, you're saying?
Like a big delta, like a big river delta, basically, or a beach, or a landslide. There's different variations on the theme of sediment hitting the edges of this lake and then all the energy of that moving sediment drops out, and so you end up with basically a big flat bench. But yeah, sandy.
Why that was so big and vast and flat.
We're going to go down a little bit farther south. We're going to take a turn up Bolduc Road and go to North Branch Cemetery. Anybody been there? Bolduc Road?
Yeah.
Flat spot. What do you think the elevation of North Branch Cemetery is? 701 feet above sea level. Let's go somewhere else. We're going to go down here and up the Terrace Street area, and we're going to go up to like Dairy Lane, that area. Other than this hill I'm taking the picture from, has anybody noticed that that whole area is very relatively flat? So we know that these flat spots, they grow cemeteries because it's easy to put graves in sandy soil. They grow agriculture, like Ananda's Gardens, because it's easy to grow crops there. They also grow neighborhoods really well, right? These flat spots. And so the Terrace Street neighborhoods here, between 650 and 700 feet above sea level. Let's jump across the river. Now we're on Route 12 South. And what's the name of the neighborhood like down below Westview Meadows? Is there a name for that? You know what I'm talking about though? I don't know. I wasn't sure if there's a name like the Meadows for it or something like that. Is there a place name? No. Okay. Yeah. But you know where I'm talking about, right? So again, super flat here, right? 695 feet above sea level is this road. So now there are red herrings out there. There are places that you'll find in Montpelier that happen to be flat at 695 feet or 700 feet. There are places there, so you can be thrown off. But you know, it's uncanny that you find a lot of these spots right at the edges of Glacier Lake Mansfield. We can go to other spots. We're gonna go back up to Sanders Circle now. So up past Anonymous, up Horn of the Moon Road, Sanders Circle, and now we find some flat fields that are right at the shores of Glacier Lake Winooski, a little bit higher up. Continue down the road to Jacobs Road, heading actually this is Gould Hill Road, heading down towards the Nature Center this way, so heading west on Gould Hill Road. Suddenly it gets very, very flat here. This is right at the shoreline of Glacier Lake Winooski. So
the Seatses have a huge sand pit.
Yes, absolutely, that is one of them. And I figure that not everybody knows where Stephen Seats lives, so I didn't mention that one. But yeah, right at Gould Hill Road here, there's a perfect flat bench that is part of this story as well. Yeah, so just pull up Google Maps and just look around and see what you find. And I want to encourage everybody that this is the beginning of a citywide scavenger hunt to find more examples of this stuff because it's super fun. So now I want to leave you with one last fun thing to think about in terms of Montpelier's glacial history. Montpelier is nothing if not a good place to go and look at bricks. Right? We have a lot of bricks and a lot of brickwork. Brick is made of clay with a little bit of sand mixed in as aggregate, right? And just because the bricks are red doesn't mean the clay was red. The firing of a brick oxidizes the iron in it and turns it red. So just because you have a red brick doesn't mean the clay was red in the first place. Our clay around this area is all, it's clay colored. It's gray, right? And so I want to just think through something with you, which is a lot of the buildings here in Montpelier were built long before the railroad was put in. And just like it's very difficult to move rocks very far, it's also very difficult to move a ton of bricks very far, at least enough to build big buildings. And so back before railroads were connecting us all, it was generally kind of the rule, more than the exception, that bricks were made from materials that were found locally, that were fired locally. Let's look at the Vermont Mutual Insurance building next to, between the theater and the post office, right? The building was built in 1826. If you look up close at the bricks on this building, they're just a mess. Look at that. See all the sediment and aggregate. There's particles of all sorts of different size in this, right? This is old brick. And also look at the shape of the bricks, right? Of all the ones that are facing kind of horizontal, the ones that are like spanners, look at how they're all slightly different sizes. Some of them warp up and down. Some of them are rounded in the corners. These are handmade bricks that were made from local clay. Now, we were talking about what happens at the edges of these glacial lakes, right? If you go out to the dead middle of these glacial lakes, that's where all the clay and the silt is collecting, right? It's down at the bottom of, remember, if we're trying to find clay in Lake Champlain, you go out to the middle of the lake and drop a core down there. Go out to the middle of glacial Lake Winooski, and you are right over the top of downtown Montpelier. Has anybody been to Blanchard Park behind the Montpelier Senior Activity Center? If you haven't, it's a great little spot to go. It's only a couple acres. But that's right. That's this little hill right here. And that is a giant lump of clay. Now, this entire area over, like all of downtown Montpelier, would have been just wall-to-wall clay deposits. But the rivers over the last 10,000 years have cut right down through them and washed them away and eroded it away. So we don't see a lot of evidence of clay deposits right in downtown Montpelier because of the scouring effect of the modern Winooski and North Branch. But we do have plenty of clay around to build buildings with. I don't know for sure that Blanchard Park, the hillside of Blanchard Park, was a site where clay was excavated from to make bricks to build the buildings in downtown Montpelier. Could be. And I would love to know if anyone has more information on that, because that would be super exciting to find out. But I think it's very cool that our brick buildings, our older brick buildings in Montpelier, are built out of the lake bottom sediment of glacial Lake Winooski. And so we were looking around downtown Montpelier at our glacial history around us everywhere. This is the Rialto building across from Capitol Grounds, right? And this is the brick there. Much more consistent grain size, but still really irregular shapes, right? See how this brick is kind of bends upward here, and these bricks are a little bit less, they're not super consistent. So these are, again, old bricks, but from a different clay source, or a different aggregate mix that was probably still local, based on when this building was built, but not from the same place as the insurance building. How about the building that Bear Pond Books is currently in? This is zooming in on these bricks. Look at what these bricks are made up of here, right? Old building, messy brick, wild clay, right? Compare that. Remember how we looked at Bethany Church after all the rock stuff? Compare that to the Skinny Pancake building right now, and look at the brickwork here. These bricks are oil-struck, or water-struck bricks. They are modern. They are made of clay sources, like extremely pure clay sources, much younger, much more modern, brought in from elsewhere. And so as you wander around downtown Montpelier looking for bedrock escarpments and whatnot, also be looking at the brick, because a brick is not a brick is not a brick. The way that brick looks can tell us a little bit about where that brick came from, and whether it is from our place or whether it came from elsewhere. So the last slide is just, I wanted to give a couple quick acknowledgments. I want to thank basically all the geologists that have done all the hard work of making this sort of thing possible to know in the first place. Stephen Wright's been instrumental, George Springston, Margie Gale, and everybody at the Vermont Geological Survey. I want to thank Charles Johnson for some of the illustrations that I used from his Nature of Vermont book back in 1998 that was published. I want to thank Walter Pullman over at UVM for some of the geology diagrams, Claire Dacey for that great watercolor, and of course the sponsors that made the PLACE program happen in the first place here, Hunger Mountain Co-op, Ben and Jerry's Foundation, and the Vermont Community Fund. So I invite everybody, well, first to join me tomorrow on a little field walk. Again, where is that happening? Gateway Park. What time? 9 noon.
Where exactly is it? It's underneath the interstate?
Underneath the interstate. Yep. So, and whether or not you can come on that field trip, I encourage you to go on your own field trip and see if you can find some of this evidence. And again, this is the very beginning of the story. I'm really excited about this idea, and I look forward to the community mind and eyes going out and seeing if we can uncover more evidence in this story here. So thank you, everybody. Nona, would you hit the lights again, Nona, please? I have some time for questions. I'm happy to stick around if anybody would like to ask some questions. Well, thanks. Thank you. Yeah.
Why does granite come in different colors?
Why does granite come in different colors? Okay, so in granite you have black stuff and you have white stuff. Sometimes you have pink stuff. So this is feldspar. The black stuff is mica, the white stuff is quartz, and the stuff that's also white is feldspar. And if you looked really close and you knew what you were doing, which I admittedly don't, you can tell the difference between the quartz and the feldspar up close. But sometimes the feldspar is pink and not white, and so that gives you pink granite. And the proportion of the mica to the quartz, the potassium feldspar to the plagioclase feldspar gives you the overall kind of look and feel to that particular kind of granite. Yeah, so our Barry granite quarries, are white and black. We don't really have the pink stuff here in Vermont.
They sell some pink. They
Oh, really?
import it.
Oh, so I don't know that. If they have pink, maybe it's from here. I've never seen the pink granite in Vermont, but I'd be excited to learn that it's here. Yeah.
So is that, when you're on the interstate, you're around Bethel, you're going north, there's that white, you're quarry with all that white. Is that a Pluton of
So,
granite?
I think that one's marble.
Is it marble?
Yeah, which is metamorphosed limestone. And without looking at the map, I'm not sure the origin story of that marble per se. Sorry.
It's called Berry White and it's granite.
They're in Bethel?
I thought it was granite.
Okay. We do have great marble quarries down in southern Vermont.
Marbles over by Rutland.
Okay. It looks like when you're driving the interstate, it just looks so shiny and bright and pure. My initial inclination was like, oh, that might be marble. But it wouldn't make sense for the story that we've been telling because it's not that far away and it is part of the same Plutonic origin story. So for the anyway, yeah.
One quick question. I know the Waits River Formation, which underlies a lot of East Montpelier, is really good ag land. And it's got a lot of line in it, I think. And we have a couple different sugar bushes that are really rich woods because they're in the Waits River.
Yeah.
What's the source of that line?
Oh, such a great question.
It doesn't seem like it's like, animals, whatever.
Yeah. So the source of the lime in the Waits River Formation is the result of a couple of different things. So that the Waits River, depending on who you ask, people have either called it limestone, they've called it marble, they've called it sandstone, they've called it limey sandstone, they've called it sandy limestone. My favorite was Sophie Veltrop with the Northeast Wilderness Trust. She calls it slimestone. I like that. So that depositional environment was, so there was two things happening. It was near shore. So there was, biotic life that was dying and stuff like that. So there was a biotic component to some of the sediments that were there. But also it's clastic limestone. And so remember at this time, the Green Mountains were eroding away into the ocean. And the first stuff to erode off the Green Mountains was all the calcium-rich stuff because that's the most easily dissolved in rainwater. And so you have all this calcium-rich sediment that's winding up in the ocean near shore, amongst sand and silt and all kinds of other stuff in this messy near-shore turbulent water. And that is the kind of the sediment that all kind of became the Waits River Formation. So it's the clastic influence from the eroding greens. It's some of the biotic stuff from it being a near-shore environment. And the crazy thing about the Waits River limestone or Waits River Formation is that you can go, you can walk 30 feet and you can find an area that's super like neutral pH soil with lots of calcified plants growing on top of it. And you go 20 feet away and you're looking at like Christmas fern and a hemlock tree, like something that's very nutrient poor. It totally depends. I love this. It totally depends on what happened that day 400 million years ago at the end of that tributary. What was dumped out into the water there. So this gets back to that like geological determinism, right? Like a bad day 400 million years ago tells you whether or not you have maidenhair fern or a hemlock tree today on a particular rock, which is great.
On the bedrock map that you had before, was Barry not on there?
Barry? Yeah, I'll show you. Oh, where's Barry on the bedrock geology map? I think I showed some. Okay, here we go. So Barry is all this stuff.
Wow. It's kind of little.
It's little, right? But it's high quality, right? So you can go to some of these plutons and you can't cut a block of granite out of it, right? It doesn't work. It's from a commercial standpoint, it's no good. Which is I think why the West Berlin Granite Company at that little tiny spot in Berlin didn't really quarry anything else because they ran out of rock that you could cut into good blocks. And so, Barry is small but mighty in terms of its granite quality.
It's not hardwood.
Where's Woodbury?
Yeah, that's what I know. Yeah, it's like Woodbury and wall of.
You'll have to help me with this. That's, let's see, that would be over here, right? Stuff?
No,
This cluster here is Woodbury? Okay, yeah. Oh yeah, because this is like Worcester. Yeah. Well, this map, if you just Google Vermont geology map, this will be the first thing that pulls up, and it's extremely high resolution, so you can zoom right into like your street and see exactly what's going on there. Yeah.
So over the years, I worked with a lot of gardeners around Montpelier, and they were all dealing with clay. And there was a rumor, which may or may not be true, that a lot of the topsoil was taken for the State House lawn, and they were left with around the outskirts of Montpelier. And in the old days, that may not be true, but in any case, they were dealing frustratingly with a lot of clay. In fact, one of my clients had so much clay, she would have to build, have engineered stone retaining walls to keep it from sliding down into their house. I mean, it was a gradual process.
Interesting. So, first I'm curious. Raise your hand if you live in Montpelier. Okay. Keep your hand raised if you have clay soils. Now raise your hand if you have sandy soils instead. So where do you live in Montpelier? North Street. So up high towards the edge of the glacial lakes, right? Right? Yeah, where the sandy stuff is being deposited. Does everybody else live
in the bowl?
In the bowl? Next to the river?
So, Sean, I live right near that Clarendon Avenue neighborhood, a flat one. Yeah, Redstone, and we have clay, really right close to what I thought you were saying was the flat areas were sandy.
Bear with me 1 second. Clarendon, is that terrace, like the Terrace Street neighborhood?
Yes.
Okay.
Yeah, that's right, they do that.
Things can change quickly.
Really fast.
Yeah, and also I'm trying to just get a slide up here that will help explain both of these things. Okay, Noni, have you hit one of the two lights, please? Thanks. Perfect. Okay, so you can end up with sand on top of clay. And if the clay gets washed off, or if the sand then gets eroded away, you're just left with clay. So lots can happen over the 11,000 intervening years. But remember, if let's say, okay, we're going to go over to Clarendon now, we're over here, right? So we are way out in Glacial Lake Winooski. We're way out in the middle of the lake here. The shore is way up towards Portal Road, right? And so over here, the first thing that's depositing on top of the bedrock is clay or silt or just fine sediment that a gardener would interpret as pretty clayey stuff, right? And then when the lake level dropped, that same exact spot is now much closer to shore, getting much coarser sediments deposited directly on top of what was the clay stuff. So you can, and then as soon as, then when you go down to Glacial Lake, Vermont, well now the tributaries are just running straight through this, and now they're carving down through all that sediment that they just put in place. And so you can have a cross-section where you have different types of sediments depending on where you were in relationship to the various different edges of the lake. So the clay that you're seeing is probably clay from Lake Winooski, Glacial Lake Winooski, and the overlying coarse sediment has been sloughed off or something like that. Yeah. But I also have not dug like a test pit out in those neighborhoods, so now I really want to. Go check that out. I'll also point out that this whole field here is dead, pancake flat. I tried to get a photo of that, but I couldn't really find a good place to park and do that. But that field just up Terrace Street is a good candidate for Lake Winooski. Nona, can I trouble you again for the lights? Well, we're just after 8:30, so I want to. I'll stay up here for a little bit if folks want to come up and ask questions and look at rocks and stuff. But I do want to release those that are itching to go have their Friday night. thanks everybody for coming. And,